So we're going to go through some of the things we covered in standard level redox, so that when we're doing the high level stuff in this topic, we'll be in a good place really. But there's a bunch of skills that we learn in this topic. We're just going to make a note of what they are, and we're going to go through them each at a time now. So this is for your own sort of sake to start with. You've got to be really comfortable, and we'll spend some time revising oxidation numbers and spotting oxidation versus reduction. You've got to be really comfortable writing and combining half equations, and we're going to be able to do redox titrations. And it's really surprising, sort of going through yesterday, how good you can be at titration calculations. But it's been a little while, a bit ring rusty, so we need to practice that a little bit. That's kind of most of what we'll focus on today. Even if we get onto it, we'll look a little bit at electrolysis and voltaic cells, so electrochemical cells. But the priority is going to be making sure we're really comfortable with oxidation numbers, oxidation reduction, oxidizing agents, reducing agents, writing those half equations, combining them and stuff, right? So we'll spend a little while on this. So what we need to do, a little bit of brainstorming then. What are the rules for identifying or deciding what oxidation numbers are, if you can remember, and then I'll talk you through it. So what I would say to you is, some of you have learnt the rules and remembered them, some of you have learnt them and forgotten them. We're going to rattle through them quite quickly now. But the important thing you understand is that oxidation numbers are a way of chemists to understand what's happening in redox reactions. So reactions where there's a transfer of electrons, so where the oxidation numbers are changing, in other words. But the oxidation numbers we identify, the concept is kind of entirely made up. So for example, in a molecule, a simple covalent molecule like water, which we know, we're going to do a bit of practice on this in a second. The water looks like that. I'm going to pause the video and you're going to tell me with water what the electron domain geometry is, what the molecular geometry is, what the bond angle is, and what the explanation is for all of that stuff. Go. So yeah, just a little reminder here, you had a tetrahedral electron domain geometry, and loads of you went through Y, 2 bonding pairs, 2 lone pairs on your answer, which is good. Some of you didn't do that, but you wrote tetrahedral anyway. The molecular geometry was V-shaped or bent, or sometimes called non-linear, but V-shaped or bent. And you said that the HOH bond angle, most of you, is 104.5. The justification for the tetrahedral electron domain geometry was that the electron pairs move to positions of maximum separation or minimum repulsion, try to get as far away from each other as they can. And the justification for the 104.5 is the fact that lone pair repulsion and bonding pair repulsion is greater than, lone pair repulsion and lone pair bonding pair repulsion is greater than the bonding pair repulsion, so these kind of get squeezed down a bit from 109.5 down to 104.5. The polarity of the bonds is delta plus delta minus, and the molecular polarity is that direction. And lastly, can it make London forces, yes or no? People nodding, thumbs up, thumbs down this time. Can it make dipole-dipole interactions, yes or no? And can it make hydrogen bonds, yes or no? Good, right, fine. So, this is a molecule, it's got polar bonds, it's not ionic. So what we do as chemists is make up what the charge would be on the hydrogens and the oxygens if, instead of being a polar bond, that these electrons shift to the atom, which is most electronegative. So we kind of, it's a bit gloopy, we pretend that water is that to help us to understand what happens if water is involved in a redox reaction. That's all it is. It's just a way of understanding what's going on in a redox reaction. It's not real, it's all made up. But you need to know the rules, and everybody accepts and knows the rules in chemistry. Okay, so let's go through those rules then. Very, very briefly. If you want to write them down, you can. If you don't want to write them down, you don't need to. They're all in your notes. I'd rather you I think you didn't write them down. but what we'll do is practice a few. So elements have got an oxidation number 0, and that could be the same for F2, O2, O3, N2, or argon. That all have, or a metal, all have oxidation number of 0. Always, always, always. The rule you missed out is that simple ions always have, simple ions have oxidation number equal to charge, and so an oxide 2 minus ion would be -2. Now remember here, oxidation numbers, you have the sign first and then the number. It's the opposite way around to charge. I don't know why, but that's the convention. Hydrogen ion would be +1, and iron 3 plus iron would be +3. And it's also worth reminding you now that we use Roman numerals in the IUPAC naming system. So if we had, say, iron oxide, and the oxide was 2 minus ions, or what we should say probably is a -2 oxidation number, the iron 3 here would be a +3 oxidation number, so we call this iron 3 oxide. We show what the oxidation number is with the name, so we can work out what the compound is. You remembered some of the rules. The rule really is the electrons. You imagine the electrons in the bond going to the more electronegative element, and what that ends up meaning is that nearly always oxygen in a compound is equal to -2, but unless in a peroxide. And so, for example, here and here, oxygen, as we explained before, is -2, hydrogen's +1, +1, +1. Oxygen here in the peroxide must be -1. So peroxide is when we've got two oxygens next to each other. Hydrogen is nearly always in a compound +1, unless in a metal hydride. And so in these examples here, and in just about all other examples, hydrogen's +1, because it's less electronegative usually than the thing that it's bound to. But in a metal hydride like sodium hydride or calcium hydride, because the metal is more electropositive or less electronegative, the hydride is -1. Okay. The general rules are really important though, aren't they? So the oxidation numbers add up to charge of the species. So if it's a neutral compound like water or NO2 or something, they'd add up to 0. But if it's like water, +1 minus 2 +1 equals 0. But if we've got a compound ion like carbonate, each of the oxygens here is -2, and the overall charge of the species of carbonate is 2 minus. So for that to work, the carbon has to be, in this situation, 4 plus. Or in nitrate, each oxygen is -2. Please don't write -6 above it. Write it out 3 times. And so here the nitrogen must be +5. So what you're going to do for a bit, I think that's enough rules for now. I'm going to write down a bunch of substances, and you're going to try and work out the oxidation numbers of all of the elements in those substances. That'll keep you busy for a minute. This is banker questions in exams. You need about to do this. So elements, dead easy, 0. Each oxygen here is always -2. So I'd go through and work them, write them all above it. Now to end up with -1, if we've got -8 already, that has to be +7. So +7, take away 8 is -1. The dichromate, we've got 7 lots of -2, which is -14. It's a 2- ion, so we've got to get to, the chromiums have to add up to +12, and there's 2 of them, so each of them is +6. So this is what we call dichromate 6, and the 6 in Roman numerals. The manganate 7 is called manganate 7 in Roman numerals because it's an oxidation number 7. While I'm at it then, when I say nitrate, carbonate, manganate, chromate, what does the 8-bit tell you, please? When there's oxygen present, they're called 8. So we call this one manganate 7, dichromate 7. Fluorine is the most electronegative element, so there it has to be -1 and -1. So the oxygen in this case is +2. That's obviously what you were thinking about earlier on. He says confidently. Here it's a metal hydride, so the metal is +1, the hydride is -1. Here we've got a peroxide. Each chlorine here is +7 because we've got 7 -2s. Each oxygen is -2. We've got overall charge of 2-. So the 4 sulfurs have got to add up to +10. There are 4 of them, so the average is 2.5. In fact, what you've got is, as I understand it anyway, you've got 2 sulfurs that are +1 and 2 sulfurs that are +4. But anyway, 2.5 is fine. And over here you've got fluorine's -1. Hydrogen must be +1. And so here the oxygen is 0, unusually. Yeah, that's a slightly funky one. That's it. I think the ones that are quite difficult are in organic compounds. So we'll do one of those. In fact, we'll do a couple of organic compounds because these are often asked as well. So let's do methane. I'm showing you through the oxidation process how oxidation number of the carbon changes. So we'll go to ethanol, then we'll go to ethanal, then we'll go to ethanoic acid, and you'll see how the oxidation number of carbon changes in each of those all the way up to carbon dioxide. So can you give me the oxidation number of carbon in each of those, please? So for these, as you might have seen as you were working through it, I was doing it. So if you tot up the hydrogens and oxygens and the carbons, whatever's left. Okay, so the hydrogens, oxygens set to +1 and -2. So you can work out, you can see how the carbon is oxidized gradually as you go through the compound. So you can see, I think quite nicely here, all that stuff ties in with the organic chemistry we were doing last term or whenever it was. And you can see the oxidation number of the carbon increasing there bit by bit. People find that hard, so that's worth knowing how to do. Right, that's it on oxidation numbers. I think you said earlier on that if you increase oxidation number, that equals oxidation. I think you know this stuff anyway. If you decrease oxidation number, that's equal to reduction. You don't get one without the other. But you can write them separately from each other in half equations. So we're going to practice writing half equations for a minute. And I think I'm going to go straight in and help you here rather than take too long about it. So I'm going to do one worked example with you to remind you what to do. And then you're going to do a couple yourselves. So the first rule is the one that people often forget because you don't always have to do it. The first rule is to check that the element that is changing oxidation number, in this case the manganese, check that you've got the same number of that on both sides. That's often forgotten. The second step is to balance oxygens with water. So we need 4 waters over here. The third step is to balance hydrogens with H+. So this is why lots of redox reactions are done in acid. It can be done in alkali as well often, but the IB only wants you to know how to do this for acids. And then we balance the charges with electrons. There's a couple of ways of doing this. I personally prefer the idea that you just tot up the total charge so far on the left and the right. 8 plus is 1 minus, comes to plus 7. And over here we've just got 2 plus. And then we add electrons, which are negative, to the more positive side to make them balance. So we add 5 electrons over here. The other way to do it is to recognise that manganese here is a plus 7 oxidation number, and here it's plus 2 oxidation number, so there has to be a 5 electron reduction going on. So it's a way of checking that you've got it right by doing both ways, really. So what I'd like you to do is to do some half equations yourselves. So I'd like you to do an old favourite. I'd like you to do this one. I'm going to nick a few from the worksheet I've got here. And then one from organic chemistry, where you're going to take methanol and turn it into methanoic acid using dichromate. If you can balance all of those, please. If you want any bonus ones, let me know. So the thing to do in each case is balance the thing you're changing oxidation number for, then add the waters that you need, then add the hydrogen ions that you need, and then put the electrons. The left hand side here is worth 12 plus, right hand side's 6 plus. So we need 6 electrons there, and it makes sense because that's going from plus 6 to plus 3 twice. So we've got a 6 electron change. This one here, quite a few of you slipped up here. We've got 4 sulfurs here, 2 sulfurs here. We need to double up the number of thiosulfates to start with. The sulfurs and oxygens are now balanced, so all you need to do is balance the charges. Left hand side is minus 4, right hand side is minus 2, so we have 2 electrons to balance it. This one's relatively straightforward, so all we need to do is add hydrogen ions and electrons over there. We've got 2 bromines here, so we need 2 bromines over there, which means we need 2 waters over here. And we've got 4 hydrogens now, so we need 2 more over here. And a couple of electrons. Nitrogens are balanced, so we need some water. And then we've now got, I think, 7. Is that right? 2, 3, 4, yeah, 6, 7. No, not 7. 4 add 6 is 10, right? So 10 hydrogens over here. And then we need 8 electrons that we've got. Am I being daft here? Yeah? I'm doing it quick, so am I making the same mistake? Just checking. And the last one, 6, 6, 1, 2, water here. And we've got 1, 2, 3, 4, 5, 6 hydrogens here. So we need 4 here and 4 electrons. And we worked out earlier on that methanol going to methanoic acid is a 4 electron change, so 4 electrons being transferred is a good thing. So this is all recorded, so if you missed any of that, you can go through and work it through slowly. But we need to be able to combine half equations as well. So if you're given this sort of question, I'm going to put that aside for 1 second. If you're given this question, say, in an exam, something along the lines of methanol reacting with dichromate to give, say, and that will need some acid to give, let's do methanol. to give methanal, and the byproduct there is going to be Cr3 plus. And I'm going to tell you that you're going to need some water somewhere as well, but I'm not going to tell you where. That's incredibly hard to try to balance. And I put this question to people yesterday, and I left them for a bit. And what they did is they ended up fighting this reaction, trying to balance it in the way that you were taught in year 7 and 8. But the trick with solving these is to first of all break them into two half equations. Look for the thing that's changing oxidation number. So the carbon is changing oxidation number, so the methanol is being oxidized and the dichromate's being reduced. So given that, then let's practice this idea. So which one of those two things on the left is the oxidizing agent? So the thing to do is to break it into two half equations and combine. So we say, well, methanol's turning into methanal. And to balance that half equation, we check the carbons are balanced, which they are. The oxygens are balanced. But we'll need 2 H pluses and 2 electrons to balance that half equation. So that process is loss of electrons, which is oxidation. So make a little note, that's oxidation. And the reduction that we're going to combine it with is the dichromate turning into chromium 3 plus. What we're doing. We've already just balanced this, we know how to do it. So 7 waters, 14 hydrogen ions and 6 electrons. Now the way to balance it is we're going to make sure in our final balanced equation there are no electrons. So you might remember, and some of you were doing this a minute ago, practicing it, that we make sure that we've got the same number of electrons on each side, and we do that, we just basically solve in the simultaneous equation. So in this example it's relatively straightforward. We've got 2 electrons over here, 6 here. So to get them to both to 6, we times the entire top reaction by 3 and then combine. So we've got 3 lots of methanol, 1 dichromate, 14 hydrogen ions, turns into 3 lots of methanal, 6 hydrogen ions. And notice I'm not bothering to write the electrons because we know they're going to cancel out. 2 Cr3 plus and 7 waters. That's not quite finished and wouldn't get all the marks because it's not yet been fully cancelled out. We've got a spot in this particular equation, we've got 6 hydrogens over here and 14 here, so we just take 6 off both sides and we say there's plus 8 hydrogen ions. And that's now balanced. So that process is something we're going to practice as well. And when I give you the worksheet for homework next time, there's going to be a few of those to do. But combining half equations was the second or the third skill we said we were going to work on. All right. We've got a little bit of time left just to remind ourselves about redox titrations. So let's do that first, and then we might come back. If we've got time, we'll come back to giving you some practice on some of these. So redox titrations. So in a redox titration, it's just a titration that doesn't need an indicator because the titrant, for example, potassium manganate 7 goes from a very strong, deep purple colour to very pale pink, almost colourless solution. So you can see the colour change when the end point is met. Now, it's worth reminding you, what I taught you about this last year, I think, you tend to have the permanganate, the manganate 7 solution, so usually potassium manganate 7, but I'll just write it like that, in the burette, and in the solution down here you might have something like iron 2 ions from, say, an iron paperclip or something, or an iron lump of something you've dissolved in sulfuric acid, giving you iron 2 ions. This is very strongly purple coloured, so it's very hard to see the bottom of the meniscus. So quite often with this one, you can look at the top of the meniscus just to see where you're at. to see the work out the titer, the volume change, because it's just so dark. But anyway, as the manganate 7 goes into the iron, it will be reduced to manganese 2, and it would stay, the solution down here would stay a very pale green colour due to the iron 2. It almost looked colourless. And eventually all of the iron will be used up, so the next drop of permanganate that goes in causes the solution to be coloured by the permanganate, and that's when you know you've got to the end point. So it might be you're told something like, well, there's some iron in here, it's been dissolved in acid, so it's iron 2 ions now. And it turns out when we do the titration that we needed 24.60 centimeters cubed of 0.02 mole per decimeter cubed KMnO4, which is essentially, I'll just write it as MnO4 minus ions. Right? So the question is, what mass of iron was originally dissolved up in that pot? So what was the mass of the thing that was in there? So let's work that through. The first thing you've got to do is to work out the half equations and combine them to get an overall balanced equation. And I'm going to speed that process up by just telling you, because we've done plenty of these already today. And when you combine them, you end up with 5 lots of Fe2 plus to 1 lot of the manganate 7. And just for time reasons, I'm not going to fully write out the balanced equation, but it's just this here with the electrons missing. So 5 lots of iron 2 plus, 8 hydrogen ions. Mn2 plus 4 waters and 5 hydrogen 3 ions. So just like with any titration, we just set it out. We can think of it like this. I'm not going to set it out as a grid. I'm going to set it out like you perhaps would in an exam. So we know the number of moles of manganate, 7. So we show the examiner we know what we're talking about by saying the number of moles of manganate is equal to the volume times the concentration, and as volumes in centimeters cubed, we divide by 1,000. And so we do 0.02, someone can tap this in for me, I'll be grateful, 0.02 times 24.6 divided by 1,000. And that comes to
4.92 times 10 to the minus 4.
4.92 times 10 to the 24, 4.92 times 10 to the minus 4 moles of permanganate. It's really scruffy, sorry. And from that we can then work out the number of moles of iron 2 plus, which of course, by the way, is equal to the number of moles of iron. And that is equal to, given there's a 5-to-1 ratio, 5 lots of 4.92 times 10 to the minus 4. And so if you could just tap that in for me, comes to, just show it to me. 2.46 times 10 to the minus 3 moles of iron 2. And then if all you've been asked to do is to work out the mass of iron, and you see how I'm setting it out here? It's so clear for the examiner. You know exactly what you're doing, is equal to that number mass is equal to mR times moles, or the relative atomic mass times moles. So you times that by 55.85, and that will come to 0.137, and that will be in the units of grams. So it's just a standard kind of moles calculation, just a reminder of that. And so good question really. So what would an exam question look like? So from this point of the year onwards, or probably later in the year really, we're going to be throwing lots of exam questions at you. The IB is really good at making it clear to you what it wants and where it wants it. So it will walk you through step by step, every step of the way. So I've taught you at GCSE and at IB to write kind of these equations as grids, and that shows you what's going on. But typically the IB says to you, what's the balanced equation? The next thing it will be, how many moles of that are there? Then it will say, well, how many moles of that are there? And then it will say, well, what's the mass of that then? And it will break it out bit by bit for you, which is really makes it really very easy. It means you have to sort of maybe think in the grid method that I've taught you, but set it out like I've just done now. So there'll be separate lines on the equation, but it's very clear usually the IB is saying what it wants you to do. Okay, yeah, good question. The last challenge for you is to draw and fully label a voltaic cell, 2 half cells. One of them's copper, one of them's zinc. What can you remember? This is going to be the focus of next lesson.